All right, so let's talk about that last problem off the lab, okay? I promise you, there is gonna be some version of this on the test,
Right.
okay? Now, it's not gonna be, you won't have to take this all the way through, but you do need like an understanding of what's happening. So, you've got two different pulleys, right? So this is what the setup is going to look like. So I've got this 200 gram mass on the inside, and I've got this 50 gram mass on the outside, okay? So when I let go of it, this is vital. Even if this starts wrong, everything is going to go wrong, okay? So when I let go of this, the 200 gram mass is going to accelerate downward. The smaller mass is going to accelerate upward. But so you have, just in terms of this, if you were to just look at just the weights themselves, okay, if you didn't look at anything else, forget that there's a pulley, and all you saw was a 200 gram mass being accelerated downward, okay? That's all, you don't know anything else. Start with this idea. Okay, well, what are the forces acting on it? Oh, okay. I've got gravity pulling it down, and since it's not falling at 9.8 meters per second squared, which clearly it's not, okay, that means there has to be some tension acting upward. Now, in this situation, which is bigger, gravity, because that's the direction that it falls. So, for this inside one, the tension is less than my gravitational force. Okay, and we're going to call it, in this situation, if you look how this is defined, okay, so that's going to be tension 1, okay, and that gravitational force, how this is defined, is going to be M1G. So the tension acting up is less than the gravitational force acting down, which leads you to the idea of like, oh, we can find a net force. Oh, okay. So the net force acting on this one is going to be your M1G minus your tension, okay? And again, do not make this weird. Just that's 9.8 meters per second squared. Do not make it negative, just 9.8 meters per second squared, okay? Do not get complicated. Now, that's going to equal the net force, which is going to be the mass, which is 200 grams, times some acceleration.
And that's
Okay.
all for the first one.
That's all for the first one. Okay?
Wait.
Okay?
Mm-hmm.
Now, this is a multiple choice. So if you look at your multiple choice answers, none of them involve the letter A. All of them involve the letter alpha. Okay? Because that's what you're trying to find. What's the angular acceleration of the system? So I can't have A. But what's the crossover between linear and angular acceleration?
The radius.
A equals
R.
R alpha, right? So this is going to be M1. Now, you have to pay attention which radius that you're using. So that's going to be M1R, okay? Alpha is going to equal M1G minus tension 1, okay? So I've got mass 1, just the radius, alpha, M1G minus tension 1, okay? So the first thing that you want to do is solve this for tension. So you're going to have tension 1 is going to equal something, okay? It's the first thing that you've got to do. Tension 1 is going to equal something. Now, on the outside one, so this is what was happening with M1. Now, I let go of this, the outside one accelerates upward. So over here, and you're calling this M2, and this is 2R, okay? It's the exact same thought process. If you look at M2, which direction does M2 go?
It goes up.
It goes up. So which is bigger, tension or the gravitational force?
Tension.
So the tension on 2 is greater than M2G. Makes sense?
Mm-hmm.
Got it. Good. Great. So you're going to do the exact same thing over here. So since the tension 2 is bigger, so tension 2 minus M2G is going to equal the net force, which is going to be M2A. But again, I can't have it in terms of A. What I can do is get it in terms of M2, but I'm going to have it in terms of R alpha. But what's that radius for that one?
2R.
2R. So that's going to be 2R alpha. So here's what you've got. You have two equations that involve tension. Okay? You need to solve both of them to isolate tension. This is the easiest one to isolate for tension because all you have to do is add MTG over to the other side. Okay? This is the easiest one. Literally, just add MTG to the other side. This one's a little bit more complicated, but you don't want a negative sign. So what I did is I added T1 over here, and then I subtracted M1R alpha to the other side.
Dr. Show the work, I mean, solving for T.
Huh?
Like, I just kind of below that equation. T1 equals what I got.
I don't care how you got it. I'm just telling you what I did.
Okay.
Okay? All right. So, let me reset this because I'm tired of holding it. Well, actually, I still do this. Okay. Now, let's talk torque. So, this weight here is trying to create a torque which is going to make this wheel spin counterclockwise. This one is creating a torque which is going to make it try and spin in the opposite direction. So you have a torque from here, and you have a torque from here. Now, if the two torques were identical, what would the wheel do?
Yeah.
Nothing. It would just sit there, right? So if the two torques were identical, nothing would happen. But clearly the torque from this one, the M2, is bigger than the torque from the outside. So now we're going to look at this in terms of torque net. So this is torque, not tension. Change your letter a little bit so you can tell the difference between tension and torque. So this is going to be torque 1 minus torque 2 equals your net torque. Okay? Now, what two things do you need to calculate torque?
Either force and radius.
Force and radius. Now, what's creating the force part of it is the tension. So the tension on one times that radius, which is going to be R, minus the tension of 2 times 2R is going to equal your net torque. Now, torque also equals two things. Torque also equals what?
Moment of inertia. And
I alpha. Okay? Now, at this point, I turn you loose and wish you well. So the next thing that you need to do is look up a weight. There we go. Okay? So at this point, you need to take whatever you have for T1 and substitute that in here. Okay?
Oh my goodness.
So you're going to have this big monstrosity
Over I.
times R. Okay, we'll get to I later.
Oh, I just saw the I over there.
We'll get to I later.
Okay.
Okay? Then you need to take that second big monstrosity for tension 2 and put that in there and multiply that by 2R, which is also going to equal I alpha.
Okay.
Okay? Now, what I would suggest at this point is that I would distribute the R's and I would distribute the 2R's. Okay? And then you can begin to combine terms. Now, also notice out here you have this minus this, okay? If you wanted to, you could also distribute like that negative sign over all of that. It's up to you, okay? I did. It just made life a little bit simpler, because then you didn't have to worry about all of that stuff. So, anyway, let me tell you how many points this particular problem is worth 7 points, okay? You get 1 point for choosing the correct answer, A, B, C, or D. 6 of the points come from showing the mathematical justification for it, okay? And how you solve it. Now, look at how all of these problems work. All of these answers are in the form of alpha equals something, okay? So that's going to tell you, oh, I need to get alpha by itself, okay? So just something to think about. So look at what your options are, okay? And then see, it's like, okay, what can I do to arrange this to fit for one of these? So let me give you a hint. It's not A or B.
Makes sense.
It's either C, D, or E.
So that makes sense. It's definitely not C then.
I'm just telling you, it's not A or B. It's not A or B. Now, on the test, I'm not going to expect you to go through and isolate this thing all the way to alpha, okay, and combine everything. I'm going to expect you to know the big idea. Like, okay, how can I express the value of tension? How can I use that to express a value of torque, okay? I'm not going to expect you to go through all of the algebra to get to the bitter end, okay? So, it's going to be on the test. Mark my words. It's going to be on the test. But you're not going to have to take it with the algebra as far as you did on this one. Gavin.
Are we only given all the equations we have on here? Or
That's it.
extra?
That's all you have. And any equations for moment of inertia.
Oh, so like the ones on the back of that white paper, we get all those.
If you need any equations for moment of inertia, I will give those to you. Okay? Don't memorize those. You just have to know how to use it. Okay? Do not memorize the moment of inertia equations. Now, you need to know the general idea. Oh, moment of inertia generally is mr squared.
Yeah.
So you need to know that, oh, okay, as radius gets bigger, moment of inertia gets bigger. Okay, you need to know that concept. Okay? But as far as like the actual equations, no.
Okay.
Got it?
Yeah.
Okay. All right. So on your calculations, they're on page 2. On that section where you've got, the top line, and then you've got the big boxes underneath, this is where I want to see those calculations, right? I don't have to see them for all 4 trials, but I do want to see a complete set of calculations for that first trial with the small pulley. So hopefully, you get something times 10 to the negative 5th for that moment of inertia. Okay? Hopefully that's what you get. If you don't, sometimes it might be to the negative 6th, but that's sketchy. Okay. Now, so when you're doing that experimental error over on page 3, so your theoretical value, because if that's wrong, everything is going to be wrong. You're going to use 1/2 mr squared. So basically what we're saying is that we're treating this thing as just one entity, okay? So we're treating it as one solid disk with a mass and a radius, okay? And again, here's the problem with moment of inertia, is that you can't just say, here's the device to measure moment of inertia. we can come up with a calculated value and an equation that says mathematically this is what it should be, but we don't have moment of inertia measuring devices like mass, time, distance, or something like that. So we kind of have to like, okay, does the actual reality match with this? So on that theoretical value, that should be around 8 times 10 to the negative fifth kilograms meters squared. Okay, so that should be the theoretical value that you get on number 5 on the analysis. Okay, a little bit less than that. So then on your experimental error, and notice I say in big bold words, show calculations. So you're going to take that 8 times 10 to the negative fifth kilograms meters squared minus like what you got for trial 1. Okay? So look back over on what you got for trial number 1. And then you're going to divide that by that 8 times 10 to the negative fifth times 100. Now, don't flip out on this deal if you're getting like, sometimes experimental errors are pretty big, okay, on this lab. Like if you get an experimental error of 50, 60%, don't sweat it that much, mainly because of the fact that you're dividing by 10 to the negative fifth, so you're dividing by a really small number. So if you're off by a little, it looks like it's a lot, okay? So it isn't like, you know, if Gavin measures the length of this table and he's off by a meter, okay, hey, that's a train wreck, okay? If he measures the distance to the moon and he's off by a meter, he's a measuring savant. So this is why you divide by the accepted value to get it as like, hey, yeah, we're off by, but are we off by a little or are we off by a lot as a percentage of what we're trying to measure, okay? That's why you divide by that.
Why do we use the same theoretical value for each one?
Because it's the same theoretical value. That's what you should get on every trial. Every trial should get you the exact same moment of inertia.
Every single... But why? Like when we change the radius and change the
But it's
mass.
the same pulley on each one. You're just using different masses and locations of different masses to try and calculate the same moment of inertia. So no matter where I attach a weight to it, I'm not changing the moment of inertia of the pulley.
Yeah. But we had 2 different pulleys.
No. The only thing that changed is where you attach the string to the pulley.
Yeah.
It's still the same pulley.
Okay, we just did it separately.
Yeah, you're just in one. You're tying it to the smaller pulley, and the other one you're attaching it to the outside. But you're still making the same pulley try to spin.
Yeah.
So that's why you use the same accepted value for all 4 trials. The only thing that changes is how much weight you put on the end of the string and where you put the string, but it's the same mass that you're trying to make spin. That's why you use the same theoretical value in all 4 trials.
Okay.
Does that make sense? It's not, you didn't do 4 different pulleys. All of the pulleys are identical, you just changed how you made it spin.
Got it. So then should the other 4 ones be the same then?
In theory, yes.
They aren't, but
They're not.
we did bad measuring.
Okay.
Yeah, in an ideal world, all 4 values for your calculated moment of inertia would be the exact same thing.
Okay. Okay. That makes sense.
Yeah, because you're just doing different ways of measuring that moment of inertia, but it's still the same disk.
Okay. Okay.
Does that make sense?
Yes. Thank you.
All right. Let me give you some hints on the answers, like on number 7. So basically it's either increase, decrease, or stay the same. Okay? So if you look at what would happen so let me take this one off, okay? So, what you guys did is that you guys took like that 20-gram mass and let it fall, okay? So imagine, and here's the visual. What would happen is if now I put that 50-gram mass out there on the edge, okay? So visualize this. Look what happened when it was the 20, and then look what happened when it was the 50, okay? So focus on what would stay the same and what would change. So is it still going to fall the same distance? If you look at the distance you guys have, it's still going to fall the same distance, right? But what would happen to the time?
Decrease with higher mass.
Mm-hmm.
And then, so then take that all the way through, okay? On 10A, okay? Because if that's wrong, everything is going to go wrong. So on 10A, we're saying here's an application. Okay, here's your car. Your car is going to accelerate at 5.64 meters per second squared, which is a decent acceleration, okay? So your answer to 10A should be around 16, okay? So as you go all the way through this, all right? So little check along the way. Your answer to 10D should be, and you're asked to find revolutions, okay? That answer on 10D should be around 30. And when you get all the way down through G, that last answer on G should be around 70. So 10A is around 16, 10D is around 30, 10G is around 70.
Like how much of an ish on G?
Not much. Not much. It's pretty close to 70. I mean, it isn't like 78 or anything like that, let's put it that way.
Can you tell me what C's around? Because I got D wrong, so if I got C wrong, then that mean I got.
C should also be in the 70s.
Okay, then I don't know what.
What'd you get for B?
26.79.
Perfect.
That's what I got.
And then C, I got around 70, and then I just divided that by 2 pi.
I got 76.
No.
No?
I got 82.
82.
For which one?
I don't know, we were talking about,
He hasn't done it yet. He probably hasn't started.
Why would I not just
Oh, I
divide
definitely
C by
started.
2 pi?
Okay, so, Caitlin, let's talk about this. What units is your answer for C in?
Radians per second?
Radians per second, right?
Mm-hmm.
So if you just divide that by 2 pi, what units do you still get? What's still there?
Oh, radians per second?
Yeah, you just end up in revolutions per second. You never canceled out the seconds.
Yeah. Wait. I don't know.
So look at it this way. Okay. So the car starts, here's your tire, right?
Mm-hmm.
What's the initial angular velocity of the tire?
0.
So if you were to draw an omega time graph,
Mm-hmm.
it would start at 0, okay? And then it's going to end up at about 80 over a certain period of time.
Yes.
Right?
Mm-hmm.
So it's not constant velocity because
No.
the tire is speeding up.
Yes.
So one option is that if you drew this graph, you could find the area underneath the graph, which would be measuring what?
Displacement.
Yeah, because that's radians. This is radians per second times seconds. The seconds cancel out, you get radians. True?
True.
Radians you can convert into revolutions.
Yeah.
Okay? So that's one option. Draw a graph. Find the area. Okay? You could also use theta equals 1/2 alpha t squared plus, but not time.
What?
You could also do theta equals 1/2 alpha t squared plus omega naught time.
Yes. Yeah, that makes sense.
Okay, but you have to find theta.
Yeah.
You just can't take radians per second.
Yeah. That doesn't make sense.
And divide it by 2 pi, and then, oh, a miracle happens, and the seconds just magically go away.
Got it. Thank you.
You're welcome. Speaking of which, you can also do that idea on that first multiple choice question. What's the average angular acceleration? So you could also draw a graph if you wanted to look at that. On the one with the different masses on the rod, so you have M and 2M, okay? Keep in mind that you want to find the moment of inertia of the system, so you have two things that are contributing to the moment of inertia, okay? And these are both point masses, so you don't have to worry about any weird equations, okay? So because of the fact that these are point masses and it's spinning around this point, okay? So each one is going to contribute to the moment of inertia. They're point masses. It's mr squared. Find the moment of inertia that's contributed by each one and then add those values together, okay? And that's why all of those are x squared, because of the fact that it's mr squared. Okay. Anything else on the lab? So if you have the lab done, you want to hand it in, that's great. If you want to wait and hand it in tomorrow, that's cool too. Okay? It's whatever works for you. Just make sure that you have, especially on this last big problem, okay? So to give you some perspective, this is how much space it took me to do all of the algebra, okay? So if you do it in one line, not happening, okay? Not happening.
What if I'm super duper smart?
You're not,
Oh,
Okay.
okay? I've been doing algebra longer than you've been on this earth,
So,
and it
like-
took me that much space.
is this side, and then half of that long enough?
Just as long, I just don't want to see one line, you go, oh, this is where we started, a miracle happened, and then here's the answer. I want to see a bunch of algebra.
I mean, we're getting close to Christmas. There could be a Christmas miracle.
We're not even past Thanksgiving, Skippy.
That's nuts.
There's 42 days until Christmas.
It's
I
better
don't
than
care, the
months.
countdown doesn't start until after Thanksgiving.
I agree.
So,
Countdown's been happening for like a while.
No, it
hasn't.
hasn't.
Y'all are
On,
just
on
stupid.
reels it's been happening
I
since
don't
day
care.
100.
doesn't matter.
That don't
Okay.
count.
So let's talk about what's going to be on the test.
Yeah.
Ruh-roh.
There's going to be two parts of the test. There's going to be a linear momentum part to it, and then there's going to be an angular momentum part to it. Now, if you look at just what they have in common, so linear momentum is just mass times velocity. Angular momentum is I omega, okay? Fundamentally, they're the same. They look completely different, but fundamentally you are multiplying together two things that represent the same physical quantity. Mass is a measure of inertia. Cool. How easy it is to get something to speed up or slow down. The more mass it has, the harder it is to get it to move. Then you're multiplying that by velocity. How fast is it moving? So basically you're multiplying inertia by velocity. Now, this is where this is a little bit more simple than the angular side of this. So what's the mass determines your inertia. There is nothing else that determines your inertia. So if I've got Hank, okay, and if Hank was a bowling ball, or if Hank was a square, or if Hank was a round hoop, as long as Hank had this much mass, no matter what the shape of Hank is, Hank would have the same amount of mass, Hank would have the same amount of inertia, And whether I took Hank here or if I took Hank with me to the moon, it's like, hey, Burkamp, we're going to send you to the moon. You get to take one thing. What are you going to take? Taking my buddy Hank. Okay? Taking Hank. Hank needs to go to the moon. And if it took me a certain amount of force to make Hank move, or if I gave Hank a certain amount of velocity, Hank would have the same momentum on Earth as Hank would have on the moon, as Hank would have in deep space, because it's mass times velocity. Now, moment of inertia. This is where moment of inertia gets a little bit more complicated. There's two things that affect moment of inertia. There's the amount of mass it has, so that's similar, but the other contributing factor is the location of the mass, okay? Where is that mass located? So, generally speaking, if you look as a broad idea, moment of inertia is mr squared, right? So, if you have the same mass, but that mass is located further out, it's going to have a bigger moment of inertia. So it's possible for two objects of unequal mass to have the same moment of inertia because it's based upon mass and radius. So you could have one object with a large mass that's close to the center. That could equal a smaller mass that was further out, okay? So if I look at, where'd my bicycle go? There it is. So here's my bicycle wheel. It has a certain moment of inertia, it has a certain mass, it has a certain radius. So if I took that same mass, but I made it smaller, okay? Then if I shrunk this thing down and kept the same mass, the moment of inertia would be vastly different because it would be the same mass, but it would have a much smaller moment of inertia. So if I wanted a smaller wheel to have the same moment of inertia, then I would have to make that mass much greater to have the same moment of inertia as this is further out. Okay. So the other thing that complicates this in terms of angular momentum is this idea of torque. So torque equals two things. It equals force times radius. It equals I alpha. Okay? So if you look at what's going to impact this acceleration of this tire. So if I look at this tire being at rest and I make it accelerate, what are some things that impact the acceleration of this wheel?
The mass and radius of moment of inertia.
Yeah, so one thing that impacts it is the moment of inertia. But because it's a spinning object, hidden within that thing are two ideas, and that's what we just talked about. The mass and where that's located. Okay, so those are the two things that impact moment of inertia. What the mass is, and where it's located. Okay, cool. So, what's another thing that determines the value of that acceleration?
Force.
Force. Do I apply a little bit of force? Do I apply a lot of force? Okay? So obviously, the more force that I apply, the bigger the acceleration is going to be. Now, here's the most critical thing. When you're dealing with something that spins, what you cannot use is F equals ma. Because if I apply that force very close to the center, or if I apply that force out on the edge, I get completely different accelerations. So the only time I could use F equals ma on this wheel is if I just throw it. Okay, it's like, I'm going to do the bicycle throw. Okay, that's the only time I could use F equals ma. If I'm anything dealing with making it spin, can't do it. Because the location of that force dictates the angular acceleration, which dictates the linear acceleration. Okay? Mm-hmm. So, you've got the location of the mass, what the value of the mass is, the location of the force, and where you apply that force. Now, this mr squared here is not the same as that radius over there. That in mr squared, that's the location of where the mass is located. This force times radius is where I apply the force. So the mr squared for this tire would be this radius from the center out to here. Okay, that would be that. The radius part in the torque, force times radius, that would be where I apply the force. Do I apply it very close to the center? Do I apply it way out here on the edge? Okay, so those two radius mean different things. One is the location of the mass, one is the location of the force. Okay. Now, in both situations, does momentum have to be conserved? Absolutely. It's one of the great conservation laws that exist. So, simple example.
Oh, that does do something. You throw this shit away. Why are there strings in it?
To keep it tied up, I guess.
No. Yes, I'm making questions on the answer.
So this is what's known as the Overman's sphere. Okay.
Dude, I can feel it.
So, okay, can you give that a little bit of spin?
Yeah.
Thank you.
Mm-hmm.
All right. So, if I pull this up, okay, come on, move. All right, I can change the radius of the sphere by closing it in, letting it come out. So, if I were to make this spin, what do I have to apply to it?
Force.
A torque, right? So, I can either make it spin by applying the force here, or I can do this out here. If you look at changing angular momentum, okay, changing angular momentum is the product of two things. How much torque that I apply and how long I apply it. Just like to change linear momentum is how much force I apply multiplied by time. So if I apply just a little bit of torque over a short amount of time, I don't change the angular momentum very much. But if I apply a big torque over a longer period of time, I create a greater change in momentum. Cool. Now, so what I'm going to do is that I'm going to get it spinning, and then I'm going to pull the rope and decrease the radius. Okay? So when I pull the rope, I'm going to shrink the radius. What's that going to do to the moment of inertia?
Nothing.
Smaller,
Make it smaller. Why?
because radius squared, smaller.
Yeah, because so the radius of the whole thing is going to get smaller. Okay? So I'm going to shrink the radius. Moment of inertia is going to get smaller. What's that going to do to my value of angular momentum? It's a trick question.
It's not the same.
Nothing. Why?
Constant.
Angular momentum has to be conserved. Unless there's an external force applied to it, L stays the same. So L equals I omega. So if I pull this down and the moment of inertia gets smaller, what has to happen?
Velocity has to get
You
bigger.
Ah, it's like you, right? It has to spin faster. So I'm going to get it spinning. Okay? We'll pull that.
Oh.
But if I let it out, it slows back down again. Why?
Do it again. Oh.
Because radius is bigger.
Okay? Now the cool part about this one, leave the camera on.
Is it glow in the dark?
Yeah.
Whoa.
Dude, some of my best questions. It's like it's
Is it glow in the dark?
yeah, just figured it out in my head.
So, we're spinning slow, spinning fast. So here's the cool thing about it is that you can change that rate of rotation without applying a torque because momentum has to be conserved. So I'm not touching it, but I can make it spin faster or slower by changing the radius of it. So this is what happens like with collapsing stars, neutron stars. So when they collapse, their radius shrinks greatly, but they have to have the same angular momentum. So what do the stars have to do?
Spin.
They have to spin really, really fast. Okay, so speaking of stars, if you didn't go out and see the northern lights last night, and it's exceptionally rare that northern lights make it this far south. So like I've lived in Kansas basically all my entire life except for when I was in Africa. And so, so there was what's called a CME, a coronal mass ejection, which basically the sun ejected a huge number of very, very high energy particles.
What?
And they interacted with our atmosphere, and it's kind of like making a light bulb emit light. So the reason that it happens close to the poles is that we have a north pole and we have a south pole. So the magnetic field lines are very, very intense at the north and south pole. So as those charged particles make it in, they interact with that magnetic field and they get diverted to the poles. So this is why this is called like the northern lights. Because typically you only see them when you're close to the North Pole because that's where the most intense concentration of magnetic field
What about
lines
the
are.
South Pole?
Or you can have the South Pole.
Oh.
So, but what's happened is that we have had such a massive coronal mass ejection that now, instead of only being visible up there in the northern regions, now it's all the way down into Kansas. So tonight's actually is supposed to be more intense than last night's was. So like last night, and it's better if you can get away from like the ambient light of the city. But even if you can't, it might, like last night it was kind of a reddish glow, but it looks more intense if you like take a picture of it on your phone, okay? Because your phone has a longer exposure than your eyeball does, so it'll show up better on your phone. So go out tonight, after dark, look to the north. It's better if you can get outside the city. They're predicting tonight's was going to be more intense than last night's because the atmosphere is already kind of charged from the storm from last night. So tonight should be even more intense. So one of the things I always wanted to do was see the northern lights because my dad was in the Navy and he was up in Alaska and he talked about how cool they looked at night. And I thought, I've never seen them. So, and it's weird. So I've never seen them. There was a storm last like October that had it, but the one last night was more intense than the one was from last October. So if you want to see it, go out after night, go give that a look. Okay.
I have a question.
What?
If the CME is like big enough, can it like?
Oh, it would toast our electrical grid
Yeah. And then Wi-Fi would.
and knock out our satellites.
I'm gonna steal the solar panels if that happens.
It might overload the electrical circuits and fry them. It wouldn't fry the panels themselves,
Between 10 p.m. and
but it
2
could
a.m.
fry the inverters that change it from AC into DC.
Then I'll steal the solar panels and sell them to people that don't realize that.
Okay. Well, they won't work without an inverter anyway. It won't hurt the panels, but it'll fry the inverters.
You probably have an unplugged inverter
So,
somewhere.
well, it's not that.
It's not the best time to film was 10 p.m. to 2 a.m. I'm asleep by then.
You're asleep.
That's like the best time. Like I went out there last night at 8 o'clock and it was a
I
nice
took a
time.
picture at like 7 yesterday and I can see it. I mean, if you put your phone into the night mode or whatever, it makes them really bright.
Wait, could you see it with your eyes?
Okay. Now, let's talk change in momentum. There's a whole bunch of different ways you can calculate change in momentum. One is that it's net force times time, which is like Newton seconds, which is why Change in momentum or momentum can be expressed in Newton seconds. That can also be mass times change in velocity. And that could also be mass times V minus V0. So what you have to focus on this problem, because you have a whole bunch of things that are equal to each other, is what's staying the same and what's changing, okay? So let's say, for example, you've got a car that's at rest and you want to speed it up to 20 meters per second, and it's a little toy car that has a mass of 10 kilograms, okay? At this point, you can find the change in momentum. Oh, 20 minus 0, that's 20. Multiply that by 10. I would get a change in momentum of 200 Newton seconds. Okay? Now, at this point, I couldn't calculate how much force was acting on the car because I don't know the time. Okay? So all I know is that I went from 0 to 20. I don't know if grandma's driving the car and this took 5 minutes to get from 0 to 20, or if I'm launching this car off of the catapult of an aircraft carrier and it's going from 0 to 20 in 1.2 seconds. I don't know. All I know is the change in the momentum. So, if you look at a momentum time graph standpoint, so all I know is that I'm starting at 0 and I'm ending up here at 200 Newton seconds, okay? So I don't know if that happens very rapidly or if that takes a long time. I don't know if it's aircraft carrier, catapult, or grandma. Don't know. All I know is that the change in momentum is 200 Newton seconds. That's all I know. Now, but let's talk about time. Now, if I told you that that happened in 1 second, oh, cool. Then, remember, the slope of a momentum time graph gives you net force. Cool. So then I could take 200 Newton seconds and divide that by 1 second. I have a net force of 200